My name is Giacomo Sala, and I'm a researcher at University of Geneva, and I've led the study that we are discussing nowadays. We focus on the so-called geometrical properties of quantum systems. So we consider how an emerging quantum geometry, so-called, is visible in so-called quantum materials. And the one that we specifically look at is a so-called topological insulator. In particular, it is called antimony telluride. This topological insulator, as the name says, is an insulating material in the bulk, but on the surface there are current-carrying electronic states. So they have been discovered roughly 20 years ago, slightly more. Despite this long time, they are still at the center of our research because they combine many different properties. So at the beginning, one was really interested in understanding topological physics of these materials, but as we have shown in our study, actually there are other aspects such as the geometry that emerges. So what we did was we took these bulk materials, we nanopatterned them, so we use so-called lithography techniques to imprint devices, and then we perform transport measurements in very strong magnetic fields that are millions times larger than the fields of Earth and at very low temperature, some minus 270 degrees. And this specific type of measurements gave us the possibility to probe the so-called quantum metric. It's one of these quantum geometrical features that we are chasing. So what we have found out is that electrons feel a similar kind of gravitational field in materials. They move under the action of the so-called quantum metric that behaves as a gravitational field. And not only we could measure these effects, but also control them electrically. And so this opens the door for many applications. So the ultimate goal of studying quantum metric would be to use the quantum metric to influence, to shape other phenomena. For example, we can think about superconductivity or optics, where the quantum metric is nowadays predicted to be really fundamental, pivotal. We are not at that stage of controlling other phenomena via the quantum metric, but our study sets the stage, so to say, to control other phenomena, because now we know where the quantum metric is at play. So if we talk about applications of the quantum metric, well, one of the most straightforward possibilities is superconductivity. And this is because the quantum metric is anticipated to determine the superconducting critical temperature of certain materials. And so there is now a strong hope that if we can control the quantum metric, we can also increase the superconducting temperature and has possibly reach one day room temperature superconductivity, which is one of the holy grails of condensed matter and physics in general. So this study, I think, is the archetypal example of how important can be to discuss with other colleagues at conferences. So the way we developed the idea of performing this study was just out of a discussion in front of a poster at a conference. We were discussing with colleagues, and then one of them said, "Hey, I just listened to your talk. Well, is it possible that what you observed there is also visible in my material?" So that's how the entire idea came to build upon the material availability and expertise of a colleague and our recent work on a similar topic. So the study was based here in Geneva, in the Department of Quantum Matter Physics, but we also collaborate with people at University of Salerno, people in Milan, and also ICMAB in Spain. Our collaborators in Salerno provided the theoretical expertise, whereas here and people in Spain put effort on the experimental side. So our study is really a fundamental study. We are not really looking into possible applications that could see life in a few years. Our entire research is driven by curiosity, by the desire to understand how nature works. When we are free to explore what we think is important, well, that's the point where we really discover major results, novel phenomena that eventually one day will lead to breakthrough applications. So now we understood that the quantum metric is present in topological insulators, is present in oxide interfaces, for example. The question now is, how do we really control it in such a way that the superconducting temperature can be increased? Or are there different ways of probing this quantum metric? In our study, we use, as I mentioned, transport, so electrical measurements at the end of the day. Can we use light to do so? Or can we take advantage of this quantum metric to generate so-called spin currents, so to control magnetic phenomena? So as you see, there are really many different directions that are opened by the simple observation of the quantum metric in topological insulators.